Okay, so good morning. I'm doing this video to add some little flesh to what we have on runoff, discharge measurement, and hydrograph analysis. I know the from pages 1 to 13 of the slides is easy to comprehend and understand, and you can actually look at that clearly from um, chapter 4 of the hydrology text I give to you, and the concepts are clearly itemized there. And you can read that. Please, I will implore you to read that. Um, a lot of diagrams to clarify the points, and a lot of um, simple English text to explain what the concepts are. Okay, so I will encourage you to look at that. What is a little difficult, which I felt I have to add a video to add flesh to the text, is what we call runoff estimations on page 14 of the slide. Some of these you might not have seen before, some you've seen before, but you need a little guidance to clarify that. So that's why I'm doing this video. Um, Now, we need to know how much runoff is occurring, either from empirical measurements or from direct measurements for different purposes. So, for instance, if you have you want to supply water from a river to people, you need to know how much water flows through the river, and you have to be able to determine the runoff in the river. Okay, if you want to make a dam, for instance, you also need to know how much water you'll be storing from the runoff. So it's important to understand how to estimate for runoff and the factor and the methods that we have. There are about five techniques, basic techniques that we use. The first technique is what we call the empirical formula, curves and tables. So what we have is just like we did for infiltration or rainfall intensity, we analyze the catchment for some time. And then we know that if a particular precipitation rains comes, knowing that the catchment parameters A and B, we can use that to determine how much runoff will occur, knowing the amount of precipitation. So A and B are constants for the catchment that have already been determined. So you have an expression like that. Just pay the expression, put in the amount of precipitation, the constant A and B are known. You use that to determine how much runoff will occur. Okay, so that is the first technique. The second technique is infiltration method, which we've already covered in our previous chapter. So once you know how much water infiltrates from precipitation using any of the infiltration techniques, you should either using the Horton approach or the fire index approach. You should be able to know how much runoff occurs. If you also know the runoff coefficient of a catchment, you can know how much of the precipitation will occur as runoff. So that's the second method sorted. The rational method, we've also explained that Q is equal to CIA, knowing the coefficient of runoff, intensity, and area of the catchment. You should be able to determine runoff, okay? And then the overland hydrograph technique, that is normally used for small catchments. And that is normally you have to analyze how much runoff is occurring by studying the hydrographs for some time. Further on, we use what we call a unit hydrograph. Okay, but what we'll be focusing on for today or for most of this slide is discharge measurement using what we call stream gauging. Okay, so the determination of runoff from a catchment is by measuring the discharge of the stream draining it, which is termed as stream gauging. A gauging station or a measurement point is a place or section on a stream where discharge measurements are taken. So looking at the slides that I gave you, the hydrology text, you look at a catchment like that. Hold on. You have a catchment like that. Okay. This point where you put your gauging station is what we call your measurement. Okay, which is already itemized. So your gauging station is the same as your measurement point. What are the main ways we can use to measure um, stream gauging? What are the techniques we have? So please remember, stream gauging is related to hydrograph analysis. So we are measuring how much runoff is occurring by what we call stream gauging. So Um, you know this expression already. Normally, most of the expressions are based on for stream gauging are based on fluid mechanics techniques, fluid mechanics concept. You know this expression Q is equal to AV, which is the discharge equation. So Q is equal to AV, which is the continuity equation, is what features prominently in these techniques. So the methods of stream gauging, there are three techniques. The first technique is what we call the venturimeter or the venturi flumes. Mark, I know, has already taught you what venturimeters are and how they relate to the Bernoulli's equation. You already know that, don't you? You should know that. So we set up venturimeters or venturi flumes on the stream, a constricted area of the stream, and then we can analyze the depths of flow and relate that to the discharge with respect to pressures using the Bernoulli concept. We also have what we call the weirs or anecuts. So the weirs are just small cut areas with calibration curves. I'm sure Mark has already taught you that. Calibration curves that you use. So Q is equal to maybe CD raise the power to thirds or something of something. So once you know the height of water in the weir, that is fluid mechanics. You can use that to determine how much flow is occurring on the stream. And the other method is what we call the slope area method, which is based on the Scherzi-Manning equation. The Scherzi-Manning equation is very easy to do. Mark has already taught you that. I know that because you've done fluid mechanics. Scherzi-Manning's equation relates slope of the bed, the hydraulic head, the velocity, and things like that to determine discharge. Okay. Um, then contracted area methods, which depend on the drop in water level, for instance. Sluiceways, these are normally used where we have uh, dams and power stations. Okay. Then we also have salt concentration method. This one is normally used for analyzing discharge in very turbulent or fast flowing streams. So the salt concentration method is very simple. What you do is you just create a salt solution. You create a salt solution with a known concentration, and then you pour that salt solution into a part of the stream. Once you do that, you monitor the quantity of solution injected, which you definitely do. The C is the amount of salt you've added to the solution. C1 is the concentration of salt you've added at a point in the stream, and then C2 is at so upstream. So I'm maybe if I have a stream here, if I have a stream uh, like that, okay, and make the outline red. I put the salt concentrate. I add the salt here. That becomes my C1. Then the concentration there becomes my uh, C2. And then once I get the salt concentration at these 2 points, I can set up this equation to determine the discharge, which is the Q, which is the discharge through. But normally you have to use this on very fast flowing and turbulent streams because you want the salt to completely mix up. It's very expensive because you need a lot of salt. Imagine you want to use the salt concentration technique on a place like the Volta River. Look at how quickly it's flowing and the volume of flow. You need a lot of salt. So sometimes it's expensive and can be impracticable. And then we have what we call the area velocity method. The area velocity method, as I've already said, is based on the continuity equation. So from that point, from here, from this point to that point, we are analyzing the types of methods that we use to gauge streams. But what we'll be focusing on more, which the syllabus encourages us to focus on, is the area velocity method. Now, the velocity, as I've said, the area velocity method is just based on the area of the cross section, the velocity of flow. Very simple and easy to do. So what you have is something like that. So you have a stream and you have this area, this stream, this is your cross section. So you want to measure the area of this cross section, and then you want to measure the velocity of flow in that cross section. So if you're able to multiply the area of the cross section and the velocity of flow, you get your discharge. As simple as that. Now, what you have to know is when you have a stream cross section, because of resistance and friction along the surface here, velocities are normally very low on the stream bed. So normally the optimum stream velocity is normally at the midpoint, where you don't have influence of friction on the stream bed and then influence of air on the stream surface. So you know when the wind is blowing on this surface and water is moving, the wind blowing will cause drag and will reduce the velocity. So normally we want to measure the velocity around the mid section of the section where we know that drag and friction are very low. And then if you plot uh, the velocity profile of a stream bed, you realize that the you can get the velocity. If you measure the surface velocity of the stream bed, you have to multiply it by a factor of about 0.85 because of the drag on the force or the drag force on the surface of the stream or the river body. Okay, so these are concepts you have to know and understand before you go into the business of measuring with doing stream gauging using the continuity concept. Okay, so what are the ways? So first of all, so as I've said, Q is equal to VA. So we look at how we measure V. Okay, definitely measuring area is easy for you because you guys have done surveying and you can break this into irregular shapes. Okay, like that. You can break this into irregular shapes like this, and you can get the area using either the trapezium approach or the Simpson's method, which you already know. So what we'll be focusing on more is how we determine the velocities. Okay, so the velocity methods that we can use, there are several of them. The first one is what we call the float or the surface measurement. So what you do here is you just put a float, either something that can move on the water or a leaf, for instance. You put a leaf on the water. Normally you want to do this at straight sections or portions of the river or the stream. You put a leaf or a float on the water, then you monitor how quickly the leaf or the float moves. So let me illustrate that. So you have put the float on the water and you monitor how quickly the float moves. So when you put the float down on the water, by the time it starts, you start your stopwatch and then you measure it across a stretch. So when you get to a point you want to stop, you stop your stopwatch, knowing the distance along the stream boundary or the borders or the bank. You can be able to find the distance, you divide that by the time, you get your velocity. Okay. So once you do that, you can determine the velocity of the float or the leaf or whatever technique you are using to determine the velocity. Okay. So there are different types of floats. You can either use surface floats or you can use poles or ropes, which you can move easily along the stream bed. Okay? So once you have the distance over time, you divide the distance over the time to get your velocity on the surface. But remember, there is drag on the surface. So you multiply that by 0.85 to get your velocity. Your velocity is 0.85 vs. Your vs is the length of the bank divided by the time. That gives you your velocity. You can also use what we call the velocity rods, which you can put on the stream into the stream. So that one is not a leaf. What it does is it can move and record, and you can make fixed reference points. So when it moves, meets the reference point, it records the distance traveled and automatically calculates the velocity of the stream. Then the other thing we also use is what we call the current meter. It's very simple. It's just a rod. It's just a meter with a rod attached. So this is the current meter. So what you have is it's like a cap. Okay, it's like a velocity. So you have something like a cap. That thing is like an anemometer with a rod attached. You stand it in the water, and when the water is passing, it turns this cap or this rod or this and then how quickly it turns the cap or the whatever funnel you're using. It turns it quickly, and then there's a meter on top of your rod that enables you to determine your revolutions. Once you get your revolution, there's a calibration curve for all meters. So revolutions are directly related to the velocity. So you multiply the revolutions by a factor to determine your velocity, and then from there you can be able to use that to estimate. Once you know your area from either the trapezoidal or the Simpson approach, multiply the two, you get your discharge. So what you have is you break the section into strips. So you break it into strips. You can either use the mid-section approach, or you use the mid-section approach, or you use the mean section approach. So what the mid-section, you break this into different blocks, irregular shape blocks like trapezoidal, and then you measure the velocities at depth 0.2 from the surface, and at depth 0.8. Okay, at that point and at that point, you add the two together and divide by 2. You multiply by the area, and you do this for each of these sections and add all of them up. The So once you do that, you find the discharge in that, the discharge in that, the discharge in that, the discharge in that, the discharge in that. You multiply that to determine your um, uh, discharge in each of these and add all of them up to find your how do we call it, your total discharge across the section. Then you can also, what you do is you multiply the b, which are the times they are each of individual depth, and add all of them up. You can either do it for 0.6 and 0.8 depth and add and for the velocity, or you can do it for 0.6. Any of them goes. You can also do it for using the mean section. So you find the how do we call it, the velocity in each of the sections, okay, using any of these concepts, and add the two up and divide by 2. And then what you do is you multiply the how do we call it, your depths by each of the mean of the two depths. So you are trying to find an average of an average, kind of. So this becomes more representative. So when you finish that, you find your V mean times your BD mean for two respective sections. You have two respective sections. You can find the discharge for each two respective sections, add all of them up consecutively, and you get your total discharge. This approach gives you a better estimate because you are doing an average of an average. You're trying to fine tune your text. Okay, you get an average of an average, which gives you a more a fine resolution reading. Um, so once you do that, um, you can do all of this in different forms and add all of them up. So as I said, a current meter always has a calibration curve. So once the stream, your current meter reads a particular velocity and number of revolution, multiply that by this constant, which are normally given by the maker or the designer to determine your velocities. Then from that, you should be able to determine your area. From that, one knowing your areas using either trapezoidal or the Simpson approach, you can be able to determine your discharges. Okay, and all of them up, you get your total discharge.